I'm really glad to be here. Thank you for having me. And I'm going to be talking about a couple years of research. It's 3 different papers, so I've just taken the author list, concatenated them, and eliminated duplicates. First, I wasn't going to put everybody on the slide, but OK, everybody's in the slide. Sorry, I keep bumping this. Some quick things about me. I have a sort of rare hybrid background where I've done a lot of pure math and have also done a decent amount of machine learning. I've been at Google DeepMind for some time now. Well, OK, it used to be, originally it was called DeepMind, and then it was Google DeepMind, and then it was DeepMind again, and now it's Google DeepMind. So it's very simple. And I was involved in AlphaStar pretty extensively, as you can tell from this iconic AlphaStar photograph. That's me. And sums up a lot. What was that? Yeah. That's all I got. So. The main thing I want to start with here is, and I'm calling this a $1 trillion question because I really believe it is, can we design neural networks with some guaranteed behavior? I mean, in a sense, this is the entire name of the game, because you can train stuff and do various things with the training itself and with the data. But ultimately, you don't have very much control over, for example, the failure modes of the network. And that really matters for a lot of applications. You really want to be able to know that certain things don't leak. One of them is privacy, right? If you're able to infer something about the data that you're not supposed to be able to infer, or various things. So there's just sort of all these different questions about making sure that the network is going to do something. And it's a difficult problem because what makes neural networks powerful is that they're a black box. So how do we reconcile this? And the starting point here is the work of Taco Cohen and others, who looked at the situation where we actually just have a group G, usually either a finite group or a Lie group, and then uses the representation theory of G to talk about what does it really take to build a practical network that is guaranteed to respect the symmetries of G, either being invariant under G or being equivariant under G with some predictable behavior. And this is sort of a really lovely field. And it matured into something called geometric deep learning, book maybe to be released this year. And that gives a sort of broad treatment of networks in this geometric sense. You know, they talk about gauge theory and this sort of thing, and they really discuss quite a few instances of this. It's a very comprehensive view of the things that are being described, namely equivariant neural networks. And I started working on a somewhat related problem in 2021, which is that we were looking at algorithmic alignment. And I'll get a bit to this. I believe I forgot what I did with my slides here. Oh no, how do I go back? There's the back. So we were trying to study how we capture certain structures that we were seeing in algorithms in actual neural networks. And the reason for this is we actually are very bad at learning algorithms in AI. In fact, transformers are not the state of the art. The state of the art are graph neural networks. And often, even on some very simple algorithms, the performance isn't very good when you go far out of distribution. So this is a really tough thing. And we were very inspired by geometric deep learning, and it really felt like the right kind of tool to be using. But it was clear quickly that it didn't really do the job. And one basic problem is a lot of the things we wanted to capture were not invertible. So groups were out, and we would need to use monoids instead. And then in other situations, we may even not have compositionality. And these lead in two different directions of generalization from groups, right? One is going to monoids, and one is going to groupoids. And then, of course, if we do both at the same time, we get categories. So this is the hierarchy there. Now, I don't have names for everything on the next slide, but there really is a third axis I'm not going to talk very much about here, which is things get operatic, and kind of think of that as like the polycategory or multi-category direction. So there's all these different ways to explore how to generalize geometric deep learning. Some of this has been done by Pim de Haan and others, but it's not that well studied. So the first of the three works that I wanted to talk about was this paper from 2002 that I did with Peter on algorithmic alignment. So, this was a notion that was introduced in 2019, and yeah, so here's the basic concept of algorithmic alignment, that dynamic programming algorithms are really closely related to graph neural networks in their overall structure. That we can have a theory that covers both of these two things at once, and that this actually leads to practical architectures. And that really is the goal of all of this, is make new architectures that are better at doing their job, at learning reasoning tasks. And this notion of algorithmic alignment from 2019, it was really about take the structure of the program and just imitate that structure directly in the neural net. And what we found is that we can get a slightly more nuanced view by looking at slightly more abstract properties of those algorithms. Because of course the problem with just following the structure of the code so tightly is you can't really capture a lot of algorithms at once that way. You might have an algorithm that does shortest path, you might have another that does sorting. So you have these different architectures, and we really wanted a slightly more universal architecture to cover the benchmarks we were looking at the time. And this was sort of the main thing that we observed in the paper, was that this phenomenon of message passing in graph neural networks seemed to have three steps to it. And those three steps were, you have data stored at some nodes, that data is sort of broadcast, and now it's out in the edges, and then something kind of happens to it on the edges where different features might interact with others, and then finally that's sort of sent into the receiving node. And it turns out that we noticed something interesting was happening with sort of the indices of the tensors when we were actually doing this. That there was something combinatorial about the indices that we could sum up with the diagram that looks like this. So we called these polynomial diagrams. I've seen them elsewhere just called polynomials. And the idea is that if we have such a thing, we can turn it into a neural network, or we can turn it into a computation by breaking that computation up into three steps. So this sort of W bracket R. Think of R here as your features object. So this might be the real numbers, or it might be something else. So then these are like W-indexed tensors, X-indexed tensors, and so on with values in R. And the first step is somehow very easy, which is you just precompose with I. Just to make sure, every single time I have presented this diagram, somebody has asked me if the first arrow is pointing in the wrong direction. It is not. What's really the question is, it's not why is that pointing backwards. It's why are the other two pointing forwards. That's the actual question. So the first one we just precompose and we get that map of tensors. So this is a tile operation. Sort of broadcasts the tensor to multiple places. And then in the next step, we sort of map into the, we're saying list. This is the list R here means the free monoid generated by R. and we then use some kind of a multiplier to combine things there. So the idea is essentially just that this top arrow is performing some multiplications. And then this next arrow does essentially the same thing, but with the free commutative monoid. As we'll see later, commutativity is a slight problem, but the free commutative monoid, and then we use addition instead.
Can I ask one thing? Mm-hmm. So, when you say algorithmic alignment, do you mean you want to construct a neural network which is optimal for a certain algorithm? Is that the...
So it's a little more agnostic than that. It's like there's something happening in the structure of the algorithms, and we're not, a priori, we're not sure what structure of the algorithm is important, right? Some of it can be learned and it doesn't matter, but some of it we think is important. And if you don't include it or don't include something like it in your network, then the network will struggle. That's kind of the basic.
So on this slide, is this still in the GNN setting? Like, what is the meaning of X, Y, and W?
Oh yeah, good point, I should say. So actually, these are finite sets. Okay, so think of these as just the indexing sets for tensors. And this describes GNNs, but it also describes a pretty wide class, at least parts of a pretty wide class of dynamic programming algorithms. So there's a couple decades, I think, of theory about dynamic programming algorithms having, in a sense, the same three sort of steps: an expansion step, a processing step, and a recombination step. So this was largely inspired by that. And I'm not claiming that this is everything about every algorithm, but this is this is the fragment that we studied here. And the first sort of interesting revelation here is that you can write any einsum this way. So the einsum has really become very fundamental compared to how it used to be. Like, didn't even used to have fast implementations of it, and now it's like half the lines of code in transformers and things like this. So the einsum, basically you pass a string like this, and implicitly this string tells you what you're going to do with these two tensors. It's saying I have a tensor of shape I times j, I have a tensor of shape j times k, and I want to somehow combine them and get a tensor of shape I times k. And it's inferred that I should do this by tiling it, so that I take each aij, I make that into an aij, but with an implicit k, right? So I make these I by j by k tensors, and then I multiply pairwise across the two copies of I times j times k, and then I sum up over j, right? And that entire process is summarized simply by writing down this diagram of finite sets with, I haven't written down what the functions are, but they should be clear. So in other words, if I write down this diagram of finite sets, I've implicitly told you this einsum operation. Now, we kind of learned something sort of after we wrote this paper that led to us starting to work with Tamarov and Glenn, which is we learned that this looked eerily like polynomial functors, and in fact kind of explained polynomial functors on a certain level. So a polynomial functor is basically just a polynomial that's also a functor. They're really important these days in the kind of applied category theory community. And it's exactly the same thing. It's just times now means multiplying sets, and plus means disjoint union of sets. And anyway, so this is how we ended up working with Tamarov and Glenn, who's an expert in polynomial functors. This is precisely what got us talking in the first place. So what's happening here is that these polynomial diagrams they're really, if you think of this as being a sort of map, an arrow from W to Z, then what these diagrams are, this is defining a category, which is really the syntax of something, or the Levier theory, if you're familiar with those, for commutative semirings. This is an old result, but we kind of found it again. So what that basically means is that providing, actually, let me add, the point here is that pre-sheaves, or actually co-pre-sheaves on the syntactic category, should be the same as some kind of algebraic thing. And in this case, it's commutative semirings. So what does all of that mean? It means that to implement every integral transform at the same time in a consistent way is actually equivalent to just giving R the structure of a commutative semiring. In a sense, this is intuitive because we're adding and we're multiplying, so we should have a way to add and a way to multiply. But and the interesting thing here is that if we look at some of the networks we were using and we look at an algorithm like shortest path, we find that the only thing that is different between the two is the choice of semiring. In shortest path, we choose a tropical semiring, a sort of min plus semiring. But in neural nets, we're typically not doing that. We're typically doing times and plus. And the quickest gains, this was already known at the time, the quickest gains you simply align the operations. So I guess this was known for plus, and we sort of discovered it for times. But it's a bit crude, but again, the issue is somehow there's not an alignment of the underlying algebraic structure. Like, it's not so easy. Even when you have the same computational graph, it's not so easy to kind of perform the same thing that R times plus is doing using R plus min or the other way around. And then this led to some other work on kind of learning the underlying semiring structure. Okay. So from that, we moved on to another thing that caught our interest, which is the notion of asynchrony. So what's going on with asynchrony is we noticed this is sort of a basic fact and sort of a deep fact, which is a lot of algorithms that are practical because of some subtle rearrangement argument, right? Finding the best path from A to B on a graph can be done precisely because you don't need to compute every path, right? You want to know the best among all the paths, but you have shortcuts that let you say, okay, well, I did this part of the computation, now I don't need to do this part, and so on. And Bellman-Ford, shortest path algorithm, is a perfect example of this, where things are absolutely as asynchronous as they can possibly be, which is that there's a huge amount of freedom in how you can implement that algorithm. Basically, you get told by your neighbor, I found a new path, I found a better path for you, and then if that's your new best path, then you update your state and you tell your neighbors, hey, I found a better path. And it sort of doesn't matter how you do this. It doesn't matter when you tell your neighbors, as long as you do eventually. It doesn't matter if you tell your neighbors things that they already knew or that are unnecessary. Like, as long as you follow some basic rules, you're guaranteed to converge to the right answer. But there's an even more deep thing here, which is that dynamic programming algorithms in practice are often not simply sort this list. It's something more like maintain in memory a sorted list, right? So something new comes in to be added to the list. You don't resort the list. You have some optimized update operation that does the right thing. And so, again, you're really thinking of this kind of data structure as responding in some way to a signal which might, there's some asynchrony properties there. So here is a picture of trying to explain what we're talking about when we're talking about asynchrony. And really, it's just any computation which is guaranteed to give the same result as a different computation. And here's like a really simple example of something like the distributive law. And if you think about algorithms like MapReduce or something like this, like they really work because of stuff like this, which is that if I know that some equation is true, then I can decide which of the two sides I want to compute. And I can decide that knowing how fast my times is and how fast my plus is. I can decide that based on where the data lives and so on. So I get more flexibility in how to do the implementation when I have these laws, right? So the mantra here is that asynchrony is really just algebra. Now that's too general to be useful, but we looked at a very particular thing. Actually, forgot I had this side note. So this is important background here on GNNs. So there are many, many, many different forms that this equation takes with slight variations, but this is the most basic one, where each node has a state, h sub v, and that is sent via a message function which updates it or changes it in some way. And then new node states are determined by a transition function that only knows about the aggregate of all the messages coming in. So a few basic properties here. The message depends only on the current state, and it depends on the entire state. We're always sending the whole state, which is a slightly weird thing to do. It's like if you wanted to implement the internet and you had to send your entire hard drive on every single packet, right? There's something very weird happening, because any notion of information being private or local has to be enforced by learnable things that might not learn it correctly. And also, you can't really define termination conditions. This is sort of a notoriously hard problem in machine learning of learning the identity function. You can manage to set something up so that the identity is one of the hardest things you can learn. So, it's because the gradient descent is always going to make you want to use all the information that you have, right? It's not so easy to learn to ignore information. And the kind of main thing here is just something very simple. A node in a graph being a relay for messages. This is just not easy to learn in the way that graph neural networks are studied. Let me add one thing here, which is, I'm not saying much about LLMs, and the main reason is they're not state-of-the-art in algorithmic alignment. GNNs are. We are actively trying to take what GNNs are able to do with algorithms and bring that into LLMs. But in short, this is a very hard problem. Okay, so what do I mean by message relay? And this is a really simple example of something that it's not so easy to do in a neural net. So say I want to just add the number 729 to the number 47, and I have the digits stored in some registers or whatever. So it's clear how to do this. I add the 72 and I carry the, I add the 729, the 7 becomes a 6, I carry the 73, right? Everything makes sense. But notice, we do have some algebra here, because every time I do an addition of two things like this, there's always two ways I can do it. I can add the 7 and then add the 7, and I get a 1 plus 1 carried, right? Or I can add the entire 14 and I get a 2 carried. So you might think this is pretty not special because we learned this in elementary school, but actually, if we think about this slightly more generally, something highly non-trivial is happening here. If we assume that our node has a set of states which is a vector space, it's a reasonable assumption in a neural net, and the set of messages is linear transformations of S. That's maybe a stronger assumption. They could be different kinds of they could be translations or other things. And now, if I have two messages, they induce a composite transformation, right? Now, asynchrony here means, do one, then do the other. But it's the same as doing them at the same time. And this is not at all a trivial equation. It's not at all straightforward to satisfy this equation. The one for the number wheel can be constructed because we have this exact sequence of abelian groups, right? That doesn't split. Okay, so somehow the non-triviality of this sequence is the only reason we're able to even get an interesting carrying operation like this in the first place. And we can rewrite this by currying. And it turns out we get exactly the one cocycle condition. This is one cocycle condition with non-trivial coefficients. And this is a right one cocycle. Before somebody may ask, I thought it was H2 that classified these extensions. Why are we using H1? And the short answer is I don't know, but they're closely related. This is H1 over Z100 as opposed to H2 over Z10, if that helps. And it turns out that thinking this way actually accidentally brings us back to geometric deep learning. Because if we now think about a Lie group acting on a manifold, and when we look at the smooth functions on that manifold and how they're transformed by G, the zero cocycles are just the G invariant functions, which are one of the most important constructions in geometric deep learning. So in a sense, this carry equation is sort of a higher order form of invariance, of the same kind of invariance being studied in geometric deep learning. Okay, so we got very excited here because it seemed like all we had to do was write down an interesting exact sequence of connected Lie groups, and we would have some interesting neural net. Because of course the problem is you can't do gradient descent on number wheels, right? We want gradient descent. We want everything to be continuous. So what's the problem? Well, here's what we tried. So this is the simplest example. The Heisenberg group of upper triangular matrices with unit diagonal lives in such an exact sequence. So this means that there exists an implementation of a kind of asynchronous message passing network where sort of the messages live in the Heisenberg group and they act by translations, by state transitions on R2, which are translations, and then the carries occur in R. And there's actually a more interesting example with where the base is a simple Lie group. This is a pretty fun one because somehow the hop vibration is involved. So if you want to talk to me about this later or ask a question about it, that would be great. But I won't say too much here, except I needed some help on Stack Exchange to figure this one out. So in short, there's a certain way that sometimes you can use cohomology and fibrations to kind of infer things about certain non-compact Lie groups. So the issue here, though, is that there aren't really any abelian examples. And as I mentioned before, like we're really assuming that message aggregation is commutative. So this wasn't as practical as we thought it would be, but it's work in progress. Maybe there's a way to consider a restricted class of problems where commutativity isn't as important. This is something that's still being tried. Basically, there's not enough abelian Lie groups. And it's pretty disappointing, actually, because it's so easy to make these non-trivial examples in the discrete case. Yeah, like literally any non-split exact sequence of abelian groups. All right, so that's the sort of second thing that I wanted to talk about, and maybe this part will make this all seem a little bit more connected. So this was a pretty big undertaking, and it was our attempt with external collaborators, external to Google DeepMind, Bruno Gavranovic and Paul Lessard. And the main goals were to sort of draw a box around everything that we want to be talking about in all of this theory. And that includes all of what I've said here, but it also includes some other things I haven't mentioned, like sheaf neural networks, which is another field of research in neural net architecture. And we wanted to have something that could have the expressive power of GDL, geometric deep learning, and also kind of capture some of the other stuff we were thinking about, carrying polynomials and so on. And the basic idea here is to replace group actions with monad algebras. So the point here is instead, a group action is a map G times X to X, but more generally we can have a monad algebra where F is some endofunctor with structure, a composition law and a unit law. So this is a very, very general thing. In fact, we know it's too general. We know that general monads are intractable and also probably not useful. But it at least provides a kind of prescriptive and consistent framework for how to approach symmetry in this broader context of algebraic structure. Now, this is known. It's the sort of monadic view of programming is obviously very well known. The bit that's maybe a bit new here is introducing parameterization. So the idea is just we need to keep track of the fact that everything that happens is happening with respect to some set of learnable parameters. And to make this work, it's not really enough to deal with categories. You have to move into the language of two categories. Maybe more generally, enriched categories. So, a two category, I just mean sort of something where you need to keep track of arrows between arrows like this. And the arrows between arrows, again, these are reparameterizations. So it may be that two arrows, two different ways of mapping tensors to each other parametrically. It may be that they're sort of the same, but up to a relabeling, right? Maybe, for example, you have something that's parametrized by 2 parameters, and you have something else that's parametrized by 3 parameters, but one of the parameters doesn't do anything. Then there's a map kind of showing that those are, in some sense, really the same.
So, just a question. So you're trying to use 2 categories to describe the algorithm that you then want to make a neural network for. The 2 categories describing the algorithm, right? It's encoding the algorithm. Is that right?
It's, I mean, on the most basic level, the category is sort of just the arrows are neural nets or something like that, right? There's sort of ways of parametrically mapping from a set to another set. So that encompasses quite a lot. The 2 part isn't really needed for the algorithmic side, at least, well, it looks like the 2 part may not be needed for the algorithmic side, but interestingly, the example with cocycles, the carrying stuff, that actually has a very nice formulation using the 2 category bit in a slightly different way.
So for the 1 category, for every morphism you consider a neural network? Is that how it works?
In the 1 category setting, it's just sort of, it's based, the base category in the 1 category setting is just set. usually. So that's just the starting point. So you just consider a program as being a function from a set to another set, right? But that's not what ultimately you want to be thinking about programs in terms of functors and so on, because the sets don't have much structure and so on, right? But you think of a set as the set of states, right? And so in principle, a program is mapping a set of states to another set of states, but that's, bringing in the functors is what gives you the structure, the algorithmic structure and things like that. So everything that we said in the first paper, so with the polynomial diagrams and so on, all of that can be done in one categories. But then the asynchrony bit, for some reason, you have to, maybe I could explain that at the end, but it's somehow there's some two-categorical trick to get the one cocycles out. Yeah, because those are sort of higher order arrows in a sense.
But are you saying these cocycles are the ones that inhibit the network from performing well?
So the problem is testing this claim. So it's a very attractive claim to say, like, here is a network where one of the inputs is a cocycle or one of the parameters is a cocycle. It's very tempting to say our choice of cohomology class should affect the qualitative behavior of the network in some way, right? That seems like a very compelling conjecture. And after we wrote this paper, several people have come to me with this conjecture, right? So but the problem is testing it. In order to test it, you need to produce a non-trivial cocycle compatible with gradient descent and build a network around it. And the ones that we had been building, really, in a sense, it doesn't make a lot of sense to have the aggregation be non-abelian. So the question is then, try it anyway, or in some way figure out how to repair the examples, or look at something that's a little bit different from how GNNs have been normally thought of. So, but I would love to see that. I think I have a strong suspicion that if you successfully implement something where you have a choice of cohomology class, that will be important. I think it's just intuitively, like for number wheels, right? Your goal is to make Z mod 100, and all you've got is copies of Z mod 10, right? It's pretty clear that if you use a trivial carry, like the zero cohomology class, that you won't be able to do it, right? So there should be a corresponding thing in the neural network world. But somehow there's a few people looking into this, a couple grad students, some other people, but so far we don't really know much about this. Everything I'm saying is a work in progress. Maybe I should just add that. But okay, so how does this kind of thing work? The one example here of how we're able to do more than just talk about geometric invariance and so, or group invariance, is, and this is a sort of basic example, but you can you can read off the interface for a recurrent neural net simply by writing down this functor and saying, well, like the free monad has algebras, and those algebras are supposed to be RNNs. So like one interesting thing to do here would be dig in and say, well, what like LSTMs are a type of RNN. So what extra structure do we have to put in and so on to get that? We don't make many prescriptions in this paper about how to actually make these networks, and that's because it's not possible. There's monads there are some really bad monads, and comonads, which we also treat, are even worse, because there you have sometimes existence issues with the co-free comonad and things like this. But you know, so we're not done, but it's the task now is to work out exactly which parts of this are important, and to better understand why it is that the group case is so nice or it's so tractable, and maybe figure out some of the other tractable cases. So one thing that we've noticed is, again, we have a sort of view of monad algebras. We have another view of comonad co-algebras. But it may be that we really need to be thinking about both at the same time, which, again, work in progress here. And I'll add that this paper actually got a startup funded. So at least one person felt that this was very likely to produce practical networks. Not the $1 trillion I mentioned, but you know, it's a start. And I guess I'm done a little bit early and can take some questions.
Questions?
Yeah.
Thank you for the interesting talk. Do you think, like, if you have a Canton algorithm, something like this, asynchronic algorithms can have?
Sorry, if I have a what?
Quantum computing.
Quantum computing. Yeah. Okay. I can't say anything like for sure on this, but I kind of feel like neural networks are very similar to quantum computers, right? In the sense that they're sort of fundamentally tensorial. So I would expect it to be much easier to model a quantum algorithm in a neural net than in a classical computer. But I don't know anything specific about this. It's just an intuition. Yeah.
Have you ever thought about studying some categories with A-infinity structure or something like that?
Well, we took a while to work up to n equals 2, and we're considering n equals infinity. If I remember my infinity categories, E infinity, that's like the generalization of rings to infinity. Yeah. So yeah, in a sense, there's already something to be done here with like two categorical, like E2 rings or out, whatever the. there should be something even in the two categorical case. So for example, set. Like set is sort of a commutative ring. But it's like it lives in a two category. Yeah.
More questions? Well, if not, let's thank Andrew.